So I think we have Jags and Bruce Graham up next. Jags has a company called Latent AI, and Bruce, my friend who has introduced Latent AI to us, will be introducing them on screen today.
Hey guys, this is Bruce. I've known Howard. I've had the pleasure of knowing Howard for 4 or 5 years now through this event. As I was saying earlier, the first project that Howard and I overlapped on, CellLink, is the money just hit the bank today from 3 out of the 9 investors raising a nice Series C momentum in the electrification battery pack space. I've been in the venture business since 1991 after the 80s, being building chips with Intel. I've been fortunate enough to be involved with about 50 projects. A third of those I backed while I was at Bessemer Venture Partners. I've transitioned to being more of a kind of a mentor, chairman, angel, helper. Jags and I worked on a project which we sold to Analog Devices in 2018. That project was an edge AI project. And Jags and I learned a lot of challenging lessons on how you get people to buy and implement edge AI and what are some of those obstacles. After that project got sold, Jags found a technology out of SRI, which I'll tell you about, which really helps to be kind of a push of the button implementation for AI at the edge. And that's the basis for Latent AI, a project that Jags and I have been working on together since early 2019. Take it away, Jags.
Thank you, Bruce. Appreciate it. Howard, thank you so much for having us over here. And let me share my video. All right. Okay, so when everybody thinks about AI, everybody thinks about those bounding boxes, right? This is what we've been very used to. So let's take you beyond the bounding boxes and explore the world of AI from the latent point of view. Automotive has completely transformed in the last few years. It's become the most expensive consumer electronic device. And you can see this happen at the CES, Consumer Electronic Show. In Vegas used to be about, your little Palm Pilots and your calculators and stuff like that. But today, if you go, the largest expo halls are about automotive, because your automotive device has become the largest consumer electronic device. You are going more from a transportation. Your car used to be either it was for a show or it was for a purpose. You took your car from point A to point B. Either it was for a commute and stuff. Totally from a transportation perspective. But we are expecting a lot more from our transportation today. The experiences are completely different from each and every individual, right? There are folks that, in Tesla, they're playing video games while they're waiting for things, whether the car is charging or not, right? And then if you look at another automaker in China, they've got this full widescreen in front of the dash. I forget the name. I think it was, forget the name of the company, but they've got a widescreen in front of them. Right. So similarly, the experiences are changing, and then automated driver assist functions are also changing to accommodate to the consumer demands. Right. All right. With all of this, right, how many sensors have we put into the car for knowing what's outside, what's inside, and also in the engine compartment, as well as on the battery packs and stuff? We are collecting almost close to 4 terabytes every hour. Imagine if you were to, use the connected, the case analogy and put a SIM card and try to send this 4 terabyte of data outside. I don't think it'll be ever possible to send that amount of data on a consistent basis and get consistent telemetry out of it. We've got to start putting in AI models, right? One of the things that AI has helped solve is, how do you arrive at meaning that was never understood before? Human mind is only capable of connecting so many dots. The system is able to connect a lot more dots and get a lot more intelligence out of it, right? That's where AI comes into play. So how do we put, with all of this data being collected, how do we put AI into the car, into the edge devices where the data is getting generated, and drive intelligence out of it? That's where latent AI comes in, right? So we are enabling edge computing to support adaptive AI. We'll talk about adaptive AI as I go in. Think about it, right? Like, when you have a robot that has multiple sensors, it's got tactile sensors, it's got temperature sensors, it's got vision sensors, and then there is a central computing within the robot. How about we, instead of sending all the sensory data to the central computing to do the processing and to come up with meanings, why can't we push that processing out to the edge, to the sensors themselves, and create a sensory network that can do intelligent work? We could do this same thing with the automotive, right? Like you have a lidar, right, radar and camera doing some of the segmentation work up front for the car to understand what's going on in front of it. So you could do that as a sensor fusion module right there, right? Things like that can be done using adaptive AI, and I'll go into this as we go. Our journey so far, as Bruce mentioned, we are an SRI spinoff. This technology that I'm Latent AI is based out of was developed for DARPA. It was funded by DARPA for a naval research project, and it was built at SRI. My co-founder and CTO, Sek Chai, built this technology, and he was at SRI for 10 years. We came out of SRI in December of 2018. We had our seed fund led by Steve Jurvetson from Future Ventures. And along the way, we had several validations. We won the IoT World Startup of the Year award in 2020. We were one of the 20 contestants, finalists at the TechCrunch Battlefield out of thousands that had participated globally. We were also the one of the top 10 edge AI innovators that were presented by Gartner in their document on edge AI. And we won Frost & Sullivan's top edge AI company of 2020. Right now, we've got our 1.0 product out. We are engaged in several evaluations from automotive to defense sector and also in the industrial floor as well. Okay, so we talked about the amount of data that is getting within the car and other areas, right? Like one other fact that I would mention here is the entirety of internet was 22 exabytes in 2002. Today, we generate that amount of data in 4 hours in the internet. Forget the car. The car was never in the picture of collecting or generating that much data that would go into the internet or to a cloud processing, right? Data is also being compared to oil by economists, right? Like a few years ago, economists called data as a new oil. If we were to draw a parallel between data and oil, can we use a similar principle of extracting value out of oil, right? You have the distillation tower, you send the oil up, and you can extract different products from different layers in the distillation tower. Similarly, our proposal is, can we build a data distillation tower along the edge continuum? For us, edge continuum starts from the sensor all the way to the core computing where the majority of the processing is happening today, right? So our goal is to build AI, build AI models that can be deployed at the very end of the sensor and all the way along the edge continuum into the core of the network or core of the computing, right? We provide software development kit. Our set of tools are divided into build and runnabilities. Build is where we help AI engineers or developers to take and build models, and we help them compress, train and compress for the right size hardware, and compile and optimize them to run efficiently on any target hardware. Right? We can support GPUs, CPUs, ARM type processors, microcontrollers, ASICs, FPGAs, and DSPs and such, right? And then the bottom half of our value prop is that we help you run these models efficiently and secure them and connect and manage them as we go, right? I will jump into a little bit of the technology side as we go. So the train and compress slide, what it allows is today, if you take any neural network, any deep learning network from an AI perspective, is represented in 32-bit floating point numbers, right? And each one of these models have about 600 to a million and multiple millions of parameters that does the computing. Our compress framework takes these 32-bit floating point numbers and converts them into integers. We can represent the same value into 8-bit integer and below, all the way down to 2-bit and 1-bit, and still not lose accuracy. The model accuracy is maintained. And then we can take that network model that's compressed and compile it. And we can compile it in such a way that today in a general model, if you have 100,000 parameters or a million parameters, you will have to load all the million parameters and compute them for every single frame. For example, in a computer vision application, every single frame you see, you need to do that. In our case, we can gate it in such a way we can run away with 30% to start off with, and then throttle it up as we go. On the runtime perspective, adaptive runtime, we can load certain models, we can load certain modules, nodes of the model, and run it efficiently. Think of, when you're driving from an ADAS perspective, right? If you are on the highway going at 60 miles per hour, suddenly an object comes in the view of the car. You don't need to identify what that object is to stop. You know it is an obstacle and you need to veer off, right? So our adaptive AI will run with that functionality of, okay, that's an object. I don't care whether it's a cow, car, or dog. I'm going to move, and then later on identify, okay, increase the processing to figure out, okay, was that a car? Was that another motorcycle or something like that? So that's the adaptive processing. And then we have connect and monitor, where once these models are deployed, staleness is going to be a very, very big problem that's coming up in the AI and deep learning world, right? You train the model with something, the data that you collected last year. And then once the model is deployed, the world is continuing to change. You need to adapt, learn from that, from the new data that you're collecting, and you've got to keep your model up to date. That's what our connect and monitor helps you do that, right? The other things that we do from a security perspective is that if you develop a model and you're deploying it, today you're not sure if the model deployed is the model that you developed. We are able to put in security watermarks on the model themselves without affecting their performance, and be able to securely validate whether this is the model that we've generated. The other technology innovation that we bring about here is we can take some of the hardware constraints up into the training cycle. So for example, if you're running on an FPGA supports routing from a data computation perspective. What that allows us to do is we can take the parameters and encode them in powers of 2, 8, 4, 2, 1 at the lowest level. During execution, we can do bit shifting rather than multiplication. That helps in faster computation. So all of this, I'm coming into one of our applications that we've built for a customer, and we are working with them right now in training with their own data and building a mini ADAS system for their backup camera. So this customer wanted to put object detection and automated driver assist or automated braking from a backup camera perspective. And the bill of material perspective, the chip they want to target was an A53 grade, which is equivalent to a Raspberry Pi, right? Automotive grade, of course. It's got very small cycles, and if you run your regular AI model, you would probably process about 2 to 3 seconds per frame. Keep that in mind, right? 2 to 3 seconds per frame. If you run that, and if you're backing up with that kind of speed, you'll probably run over somebody before your system will realize that an object or a person is there in that. Using our technology, we were able to build a model, compress it small enough, and compile it, and run it at 30 frames per second. right? So 30 frames are processed per second in that process, and they're able to achieve their goal of identifying what it is, right? So we are able to achieve this, and the customer is building their own model using our toolkit. We provide SDKs, software development kit, as I said earlier. It's deployable on the customer side. We don't get to see the models or data. The customer just uses our tools to compress and compile their own models and deploy. So that's what we do. We are working with factory customers as well. We're working with the company's manufacturers, where we are helping them run more models on their GPU. It's not just for embedded processing, it's also on the higher end. They want to run more models and faster in trying to get that quality control processes done, right? All right, that's pretty much from my end. Howard, any questions? You're on mute, Howard.
Sorry, we're running out of time, Jags, but I thought it would be interesting to at least have you mention a few of the other use cases or applications that you have, because I thought it was very fascinating how many different places you could be applying yourselves. You want to just mention some of those?
Absolutely. Absolutely. I will talk about a QSR, quick service restaurant use case, right? People would be scratching their head, how is AI applicable in a QSR? So this restaurant has a high quality standard for their product that's coming out of the fryer in the kitchen. So for example, fried chicken can only stay 20 minutes on the shelf. After 20 minutes, it needs to be thrown out because they believe that the quality, taste quality degrades. So they've built a computer vision model that monitors the product comes out, timestamps it, and if it crosses the 20-minute mark, it alerts them to throw it out. Second use case, they have a camera pointing through the drive-through and looking at the types of cars and the number of cars that are coming through. So based on that, they can do demand generation for demand forecast for the kitchen. So how many chickens to put, how many nuggets to put, and all that stuff. And then the third use case is that they want to do quality control check on the drive-through bagging. They want to compare the point of sale ticket with the what's going into the bag, right? You don't want Jimmy to be upset 1 mile outside of after crossing the restaurant that his nuggets are not there, right? So they're using computer vision to monitor what goes into the bag, compare it with the point of sale ticket. So all of this needs to be done within the restaurant context. They cannot be streaming this video up to a cloud processor, or they cannot be putting a high performance computing like a $40,000, $50,000 worth of server in each restaurant. They have about 2,800 restaurants that they need to put this technology in. So they're using minimum Intel NUCs and NVIDIA Xaviers, and that's where we are helping them to run these processes on the lower end hardware.
Cool. There was much more I saw in your presentation, but I don't think we have time for it. Thanks, Jags.
Yes. Excellent. Thanks, Howard.
Yeah, that's really interesting.